Before we go into the actual calculation examples, I want to run you through some of the theory behind this area problem in calculus that we're going to be calling definite integrals. And the start of this is just to approximate the area under those curves. And I was talking about that a little bit in the last example, but we have a couple of different methods of approximating. We have them called RRAM and LRAM are going to be our two main ones, and then there's an MRAM, but RRAM is right rectangular approximation method. So if you'll see this picture down here, this is RRAM, and it's basically you make a little rectangle and the right corner of the rectangle touches on the function at each spot, at each right edge of that rectangle. LRAM is just the opposite, where the rectangle goes up and contacts on the left side. As you'll notice, in this case, the RRAM is a bit of an overestimate, the LRAM is a bit of an underestimate, and so sometimes they use this MRAM, which takes basically an average of the two, which is a better method, but it's going to be a little bit harder to use. It's a little bit more difficult to line up the points. And so generally it's just one of these two that we'll be using. So the RRAM and LRAM, we want to get those rectangles as small as possible to get better approximations, but part of what we're going to do is just talk about in specific examples which one you're going to do. That will have an effect on the answer that you get. But now let's talk about the other theory behind these, what we call definite integrals. Thinking again about those rectangles, we can use either RRAM or LRAM. It doesn't really matter in terms of what we're doing right here, but it says we're going to approximate the area under a curve. We divide our interval into n subintervals, which we're going to call delta x. That means the change in x, and that's going to be the width of each rectangle. So I'm going to have this formula down here, and this delta x is going to be right there. That's going to be the width of each rectangle. Then we're going to use the x value where we're at and use that to represent the x value at each subinterval. And then when you plug that x value into a formula, that gives you a value on the formula. And so this f of xi, that's going to be the y value of the function, and that's going to be like the height of the rectangle. So that's right here, this f of xi times delta x. This is like the height times the width of a rectangle, and so height times width is going to give us area. We're looking for area of all those little rectangles in these problems. Now, if we keep doing this, we can have many of these n subintervals and go all the way up to n, whatever n has. But we're going to put it in this summation notation because we maybe get the first rectangle, and then we go up one and get the second rectangle, and the third, and so forth until we get all the way to this top value of n, whatever that happens to be. Now, as we were talking about before, if we're going to get closer and closer to the actual value under these curves, we want these rectangles to get a lot smaller. The intervals, the subintervals that we have to get smaller and smaller, and then the sum gets closer to the actual value. That means that this delta x that we were talking about, this width of the rectangle, approaches 0, and then n, that's going to be the number of rectangles, is going to approach infinity. So tiny, really skinny little rectangles, and just an infinite number of those. When we have that, we're going to say that n approaches infinity. So the number of rectangles n approaches infinity. These are getting really small, and essentially if you go far enough, if you go to infinity, then it's actually equal to the area underneath, and that's what's called a definite integral. Now we have a little bit of a cleaned up version of a definite integral of this area stuff here. So I want you to notice in this formula, this f of xi, we're just going to make it simpler and we'll call it f of x. When we have that delta x, that means change in x, or the width of the rectangle. We're going to change that to dx when we put it in this thing called a definite integral. And then I also want you to notice that we've got two new letters here, and that's a and b. A and b are going to be the starting and ending point on this definite integral. Start and end right here. That will just basically tell us on our graph from what x value to what x value do we go. This is always the lower value, this is always the higher value when we're talking about a definite integral. So it's over this interval a to b, and that will help us in our examples coming up next. That will help us to find the area under the curve. But all cleaned up, we are going to be having this definite integral, and in the next couple of examples I will show you how to interpret this notation based on the graph, based on what they're actually having us find with these integrals.